All right, what's on the bench today? It is a crystal filter and nice big can, real nice Japanese quality. I pulled it out of an old ham radio, and I didn't want the rest of the radio, threw it away. This is just one board out of the radio, and it is a made by the Nikko Denshi company. I think it was out of an ICOM radio. I forget now. Anyway, it's crystal filter model K10F24A at 10.7 megahertz. So 10.7 megahertz is a real common IF frequency and in FM radios and stuff. And I thought I'd save it for, might need it someday. I don't know. It's labeled in, out, and then it's got some little screws that you can actually mechanically mount this thing, which is nice. And it actually had a solder blob here onto the ground, so you can make a good connection to it, to the radio that it was in. But I thought we'd talk about measuring these things, and there is a trap for young players on some of the crystal filters. So let's first talk about that. Okay, so how are you going to measure this filter, okay? You have some type of bandpass response. You're going to have an in and an out and a ground, okay? And that's all there is to filters. And so you want to do some kind of frequency sweep here. You could do it on a vector network analyzer, or if you have a spectrum analyzer with a tracking generator, you can do it that way. That's the way we're going to do it here. So here is your spectrum analyzer, and the output is a tracking generator and the in. Okay, so the tracking generator is going to come over to this side, and the in's going to come over to this side, and you hook it up, and that's what you think you're going to do. Now, that works in particular cases, but it doesn't work in other cases. So why wouldn't it work? Well, a spectrum analyzer, the input of a spectrum analyzer is always 50 ohms, okay? It's going to have a 50 ohm load. So whatever you hook this up to, you're putting a 50 ohm load on the output of the filter. And then the tracking generator also has a 50 ohm impedance. So you have 50 ohms on this side and 50 ohms on this side. So you're measuring your filter with a 50 ohm load on both sides of it. And a lot of filters are not designed to operate at 50 ohms, especially a lot of IF, intermediate frequency crystals in radios, audio filters and things like that. They're designed at a particular ohmage, okay? And in general, around, I'd say maybe 1,000 ohms to 3,000 ohms is common in my experience for the impedance of these things. 1,500 is kind of in the middle. That's pretty common for something like this. So if you want to measure in your setup here, you really should have a couple resistors in series. So let's say this is your 1.5K and your 1.5K, and then you'll measure the filter. So you'll have a input impedance. And the filter characteristics will actually change if you load them down. If it's loaded down with 50 ohms, that actually affects the shape of this crystal filter and give you a weird result. So that's what I want to demonstrate today is putting this, this should be K. So let's take a look at that. Now this is something very common, and so I've built my own little test fixture quite a while ago. I get a lot of use out of it, and it is a SMA connector on both sides, and then it has a series resistor that is a potentiometer, so I can change the series resistance, right? So let's go ahead and measure that. All right, so let's measure the series resistor that I have the potentiometer set to right now. And currently, there we go. Currently, it is set to 0.9K. All right, so about 970. Can you see that? Let me turn the light off here. So if I want to adjust that, I'm going to tweak my Tweak my potentiometer. There we go. Ooh, 1.4K. That's not good. There we go. 1.8K, 1.7, 1.5. Let's do 1.5K, okay? And then I need to do that on the other side. So we will have those two values set to 1.5K, which is just a guess. I don't know what resistance that crystal filter was designed for, but I know it's going to be pretty close to 1.5K, just from experience. Maybe I'll get lucky. 1.5 ohms. Yeah, let's see here, 1.6, 1.55. All right, so now I have it set to about 1,500 ohms on both sides, and that's where we're going to start. And we'll do that first, and then I'll show you the effects that has on the filter. Okay, now we do need to hook it up to our filter here. And so I'm going to take our little board, and I am going to find some solder. Here we go. Put some solder on these pins here. Blob there, blob there. We'll take our test board and solder both sides on. Just has to last long enough to measure it. So there we go. And then we need to hook up the grounds. So this side has a place to put a ground wire, and we will try to do that. All right, there. All right, and there is no through ground. I have to do something with this as well. So I think what I'm going to do is I'm just going to solder over to this side, and there's no place to solder onto the can. I don't want to muck it up. It'll be fine to have one side there. All right. Oops. Ah. There we go. All right, so now we have it all hooked up, and we can put it on our vector network or scalar network analyzer. A spectrum analyzer with a tracking generator is basically a scalar network analyzer of types. It's not going to have any phase information, but it will have amplitude information, which is the scalar part of it. That's why they call it that. All right, so let's put this on. I'm putting the connections on. All right, so we have the tracking generator. Here's the output of the tracking generator and the input, so our filter's in line there. All right, so we need to set the start and stop. Our center frequency is going to be 10.7 megahertz. We want to, 10.7 megahertz, there we go. And we want a span of about, let's say 50 kilohertz. Just so it's nice and wide. And then we'll turn the tracking generator on. And let's see if we get something. Ah, there we go. There's our filter. It looks very, very ugly. All right, so let's zoom in a bit here. Let's set our span to 20 kilohertz. And see if we're not seeing anything now. Now it's still looking very, very ugly. And not exactly sure why. I guess it's not, 1500 ohms is not a good value for this thing. Let's set our tracking generator level to 0 dBm. And wow, we're getting really, really weird response. Okay, so that's sort of the point of the video, is you need to know what resistance the device was set at. Let me move this into the camera view here. Okay, so I'm going to tweak these. I'm going to tweak these knobs a bit here. We will adjust them all the way to one side. So now we do have 50 ohms on both sides, I believe. Yeah. So now it's looking more like a filter, right? But this side is all messed up. So our guess was wrong. So I'm going to turn the knob a little bit, and these are slow sweeps, so you're going to have some patience. So yeah, that's a little bit better. I'm going to turn the knob a little bit more. And you can see it keeps coming down every time I turn the knob. And there, that's not too bad. You want to have these pretty straight. You don't want to have a big skirt at the two sides. And I can kind of tweak that. Oops. Oh, I just messed it up. I tweaked the wrong one. All right, let's go back. Yeah, that looks not too bad. And I'm going to tweak the other side here. And see, I'm going to go here. Yep, that's not good. This is a bit too high here, so I'm going to move my resistance a little bit. Yeah, that's about right. And now I think I want to turn this one a little bit. Oops, making that one bad. I'm not keeping track of which knob I'm turning here. Let's take a look at this one. And now it's probably too far. Yeah, let's turn it a little bit farther. That's better. We'll turn a little bit farther. So you have to have, like I said, you have to have a little bit of patience for these things. Looking better. There we go. So we'll just call this reasonable, okay? We have somewhat flat input and output, and then the lumps here in the pass band have kind of gone away. It's still going to be a little lumpy, but you know, they're minimized. So that's kind of more like the response that we would expect. If you wanted to make the right measurement, you would then measure those values of resistance that you've just put in there. You would then kind of equalize them and then do a through calibration and try to get a better response here. So let's go ahead and try to do that. All right, so I've unsoldered the wires to the filter, and I'm going to measure our resistance that we have set currently. And we are right at about 113 ohms. Interesting. So this probably is, well, let's measure the other side. Let's measure the other side too. That seems very low to me, but maybe. It's better if you have a data sheet for these things. Yeah, so this side is set to about 600 ohms. And so I'm going to set both sides to 600 ohms because that sounds like a better value to me, just again from experience. So I'll set both sides to 600, and then we will go do a through calibration and measure the filter at 600 ohms. So I think that's probably a reasonable thing to do. So let's set this one to 600. Okay, there, 600 ohms on that side. And go back to this side, make sure I measured it correctly. And let's see here. 400, oh, this side's 480. 500 ohms, maybe? 480. Did I not measure that correctly last time? Maybe I didn't. Measure twice, cut once. And 480. Okay, so we'll make this side 480 as well. And then we will do a through measurement. Okay, 480. And this side Double check. Okay, so we're okay. All right, so now what we're going to do is a through calibration. And let's disconnect this. All right. All right, so we already have the grounds connected with a wire, so that will be okay. Let's see here. Let's go ahead and put our cables on. All right. And we will then do a store ref, normalize. And now we're at 0 dBm, and I did that wrong. Okay, so we want to do a through calibration now, and we have the black wire going across, but we need to short the two. We need to short the two inputs together here. Do that with some solder. There we go. Now we have a through, and so we are going to do a store ref, normalize, and now we have everything set at 0. And now I can disconnect those two wires again, and we're going way down off the scale again. All right, so now we need to hook it back up to the filter again. All right, so let's do that. All right, there we go. We can take a look at our measurement. It looks pretty nice now. We're kind of flat, a little bit of bumpies, that's fine. Let's do our reference position here. We'll put hood it up there. So 0 is that line there. So our filter is introducing about a 5 dB loss, something like that. And now we have a nice looking filter, and we can go measure it now. Okay, so we went through all of that trouble to try to figure out the impedance of the input and the output. We made a good guess. It's not going to be perfect, but we made a good guess. So now let's go ahead and measure the, we measured the loss in the system and insertion loss, and now we can measure the filter response, which is marker functions -3 dB. And let's change that to -6. Let's see here. Oops. Yeah, about here. Set it here to about, so we catch all of the whoop-de-doos. And now we can measure the width. So this is built into the spectrum analyzer. There is a dB bandwidth, and you can set how many dB you want to measure it at. We're going to measure it here at about to -5.8 dB. And our bandwidth is 2.4 kilohertz, okay? So 2.4 kilohertz, that's a very reasonable number for bandwidth for a filter, okay? All right, so give you some ideas on how to measure these things. Let's go ahead and set these both to 50 ohms, okay? And the calibration is going to go wacky, okay, because we calibrated at a particular impedance. Let's see, your tracking generator, references position. Let's move it down here onto screen. So that's it. This is what it looks like at 50 ohms, okay? And you can sort of still get an idea of the bandwidth, so you don't need to go through all those headaches of figuring out the impedance and everything. But the shape of the filter you can see is really off because we're 50 ohms input, 50 ohms output. It's just not as pretty as it could have been. But for quick measurements, you can do it this way just fine. Okay, so let's go ahead and move it for too much impedance, and then you get something that looks really, really ugly like this. We already saw that before. You're just not going to get a good looking picture at all there. All right. Okay, and we'll stop the video here. It said a frequency of 10.7 megahertz here. It's interesting that the model number ends in 2.4. And what did we measure as the bandwidth? 2.4 kilohertz. So I think that 2.4 is not there by coincidence. I think it's 2.4 kilohertz of bandwidth. And then the K10 might be the type of 10 megahertz or just the type of filter it is. But I think it's not a dumb coincidence that 2.4 we measured 2.4 and then this is 2.4. So I don't think that's a coincidence. But there you go. Hope you learned something.